When you picture a factory floor, you're probably thinking about massive machines, sparks flying, metal getting sliced and diced with just incredible force. But what if I told you that the single most powerful force in that whole process, the one that really dictates whether a part is perfect or scrap, is totally invisible? What is this hidden force that can wear down the toughest tools, wreck the most precise work, and just waste huge amounts of energy? You guessed it, it's heat. At the microscopic level, every single cut a machine makes is like a tiny contained inferno. And it's not just some side effect, it's a fundamental part of the physics. Learning how to master this heat is, without a doubt, one of the biggest challenges in all of modern manufacturing. All right, so here's how we're going to break this down. First, we'll dig into where all this heat actually comes from. Then, we'll see how scientists manage to measure something they can't even see. We'll look at the serious damage it can cause, check out the clever ways we're fighting back, and finally, take a peek at what the future holds. Okay, let's zoom all the way in. I mean, way, way in, right to the point where the cutting tool touches the metal. Now, this isn't a simple slice like a knife through butter. Oh no, it's a violent, super fast process of deforming metal. This spot right here, the tool-chip interface, that's ground zero. The pressure is just astronomical. And the material isn't being cleanly sliced, it's being sheared and deformed at incredible speed. All that physical energy has to go somewhere, right? Well, it gets converted into a massive focused blast of thermal energy. We're talking pure, intense heat. In fact, the heat gets so intense that it can create these things inside the metal chip called adiabatic shear bands. You can think of them like microscopic scars left by the heat. They're direct physical proof that temperature isn't just a byproduct, it's a core ingredient in how the metal chip itself is even formed. So, if all this crazy heat is happening on a tiny microscopic scale and it's all over in a fraction of a second, how on earth do scientists and engineers actually see it? How do you measure an invisible inferno? This is where things get really, really clever. I mean, sure, you've got high-speed thermal cameras, but scientists have come up with some genius tricks. My favorite is the tool-work thermocouple idea. They basically turn the cutting tool and the metal part into a tiny thermometer themselves. The point where they touch creates a voltage that changes with the temperature, giving them a perfect reading right from the heart of the action. So cool. Okay, so we can measure it, but why go through all that trouble? I mean, what's the big deal? Well, when that heat gets out of control, the consequences are, let's just say, not good. And this right here says it all. I mean, just look at the difference. On the left, when you control the temperature, you get a beautiful, smooth surface and your tools last forever. But on the right, when heat runs wild, you get rough surfaces, your tools wear out and oxidize like crazy, and you can even get localized melting. It just completely ruins the part and destroys the tool. And that brings us to the core challenge, doesn't it? If heat is just an unavoidable part of cutting metal, how do you get it under control? How do you actually tame that inferno? This is where we get into the engineering toolbox for thermal management. And believe me, over the years, people have come up with some incredibly smart ways to deal with these extreme temperatures. Generally, all these strategies fall into two main camps. The first one is pretty obvious. Find better ways to pull the heat away. The second one, though, well, it's a little more surprising. So we're way past just flooding a part with coolant now. These days, we have advanced techniques like MQL, that's minimum quantity lubrication. It uses this super targeted mist of oil and air. And what the research shows is that MQL, especially with some of these new bio-based fluids, can drop the temperature way more than cutting dry, or even using old-school flood coolants. Yeah, this quote from a study pretty much nails it. Just by using an MQL system that also has a little fan to blow chips away, they cut the temperature by more than half. That is a huge deal. It means your tools last longer and your parts come out better, period. But okay, what if you need to get things really cold? Like when you're machining the absolute toughest superalloys for something like a jet engine turbine blade, the heat is just on another level. For those kinds of jobs, you have to bring out the big guns. And this is it, cryogenic machining. You're literally spraying a jet of liquid nitrogen right at the cutting zone. And look at that number. You can get a temperature drop of up to 500 degrees Celsius right on the tool's face. It's an absolute game changer for stopping heat-related damage like oxidation when you're working with those crazy tough alloys. All right, so we've covered getting rid of heat.
But remember that second strategy I mentioned? The one that sounded a little crazy? Well, sometimes the best way to control the heat is to actually add more.
It's a technique called thermal assisted machining. For materials that are extremely hard or brittle, you can use something like a laser to perfectly heat the part to, say, 500 degrees Celsius right before the cutting tool gets there. What does that do? It softens the material just enough to make it way easier to cut. It lowers the force needed, saves energy, and can turn a job that was nearly impossible into something almost routine. So, where is all this technology heading? We've seen that we can go super cold, or we can strategically add heat. But the future of managing this stuff is actually a lot more sophisticated than just turning the thermostat up or down. For the longest time, the whole game was just about getting rid of heat. It was seen as this enemy, this negative byproduct that you had to get rid of as fast as you possibly could. But that whole way of thinking is changing. Now, the goal isn't just removal, it's control. It's about really understanding the thermal physics at a super deep level and then using that knowledge to manipulate the conditions to create the absolute perfect cutting environment for any material you can think of. And that really leaves us with a pretty fascinating question, doesn't it? If we can control heat with this kind of precision, adding it just so, removing it just so, could we actually turn this invisible enemy into our greatest ally? Could we use that microscopic forge, not just to cut metal, but to actually improve its properties as we cut it, creating parts that are stronger and more reliable than we ever thought possible? Well, that quest is exactly what's driving the future of manufacturing.